Hello, BC Calculus students. This is Mr. Johnson. This is section 1.6, which is on inverse trig functions and logarithms. So what we're going to talk about is how these inverse functions relate, and we're going to start with asking the question about the algebraic relationship between them. And if you remember back to this was mostly in pre-calculus. If you took a function and you were trying to determine if a separate function was an inverse of it, if you were to insert the inverse function into the original and simplify algebraically, you need to get x. But you can't just stop there. You also have to do the opposite of that, where you take the inverse function and then you insert the original, and you must also be able to simplify to x. And this algebraic relationship is one of the ways that you can prove that two functions are inverses of each other. Now, graphically, what you're doing is you're taking a look at a function. Let's say that it's some sort of exponential function like this, and you're looking at the inverse, which would be a logarithmic function, and every point that would be on the original, whatever that would be reflected over the line y equals x and would exist on the inverse function. So graphically, that's how you would determine if you have two functions that are inverse relationships of each other. And we'll get into a little bit more of this in a second here. With the inverse function, we would like it to be a full function where we wouldn't have to limit the domain. So here's what I mean by that. Let's say that you had, for instance, y equals x squared. All right, so if you envision reflecting this over the line y equals x, you end up getting a parabolic shape that looks like this. Okay, now the issue with this, this would be y squared is equal to x. The issue with this is that the blue graph that you see is not a function. It doesn't pass the vertical line test. The reason that inverse is not the function, so let me back up here. This would be representative of f of x, and this is representative of the inverse. The issue with the blue graph is that since it is not a function, it didn't come from a one-to-one function. So the red graph is a function, but it is not a one-to-one function. So the question is, what is a one-to-one function? Well, a one-to-one function means that every y value has at most one x value. In other words, we can test if a certain graph is a one-to-one function by taking the horizontal line test. And this is just like that vertical line test, except now it's horizontal. So if we were to take this particular red function that you see here, y equals, oh, I'm sorry, I should have put x squared, I apologize. If you were to take y equals x squared and you were to apply the horizontal line test, that horizontal line can never touch the graph at any particular moment more than once. And clearly, for instance, if this was your horizontal line you were analyzing, it would touch the graph here as well as here, which means it does not pass the horizontal line test, which means it's not one-to-one. We see the ramifications of that because when we try to graph the inverse, we get a graph that is not a function. So we would have to limit the domain. So the idea here is that when you are finding an inverse, you like a one-to-one function, because if you have a one-to-one function, then the entire inverse also exists. Here's an example of it, the one that I already graphed. If you have an exponential function, let's say it's e to the x, and you have the inverse, which is the natural log of x, e to the x is a one-to-one function. It passes both the vertical and horizontal line tests, and therefore the inverse exists as well for the entire domain. Okay, let's go on to the next page. Okay, so what we're going to do here is we're going to talk about how to find the inverse of a function. And the first step is that you will be switching the x values and the y values. Once you do that, then you simply just solve for y. And that is the easiest two-step process to find the inverse of a function. How do we graph the inverse of a function? I've already explained it a little bit, but you take every point or every ordered pair on f of x and you reflect it over the line y equals x. Okay, every single one of those points would be reflected over. So for instance, if on f of x you had the point 1, -2, then if you were to reflect that over the line y equals x on the inverse, then you'll have the point -2, 1. We use this in calculus a little bit because we do the derivative of an inverse. We won't be talking about it necessarily during this section, but with the derivative of an inverse, often we need to use this relationship where these points are reflected over the y equals x line, because that is the way that we are able to get the value that we're trying to find the slope of when we're trying to do the derivative of an inverse. To show a function is one-to-one, the function must be always increasing or always decreasing. And if you remember back to section 1.1, that's called a monotonic graph. Okay, let's move on to the next page. We're going to spend a little bit of time reviewing logarithms now. And you've seen this now for a number of years, but it always gets a little bit fuzzy over time. So we have, let's say, some exponential function, a to the x, and we have the logarithm with base a. So in other words, we have the inverse of a to the x. And again, it is a perfect reflection over the line y equals x. So for instance, if you were to take this point right here, which is 0, 1, you now have the point 1, 0 on the inverse, which is a reflection over the line y equals x. So the domain of an exponential is -infinity to infinity, and the range of an exponential is 0 to infinity. With the inverse, so the logarithm, the domain is the range of the exponential. So the domain now becomes 0 to infinity, and the range of the logarithm is the domain of the exponential. So that becomes -infinity to infinity. Okay, so let's say we were looking at the graph y equals 2 to the power of x. So let's say that y is 8. So what we have is 8 equal to 2 to the power of x, and that would mean that x would be 3. If y was 16, then we have 16 equals 2 to the power of x, and that means that x would be 4. Okay, now let's say that y is 10. So we have 10, which is equal to 2 to the x, and without some sort of formula, we really can't figure out what x is. We could get a ballpark. We do know it's between 3 and 4 because we just analyzed when y is 8 and when y is 16, and of course 10 is between those two, and so we do know it's between 3 and 4, but we can't figure that out without additional information. That is exactly why we have logarithms at our disposal, because a logarithm is going to be able to analyze that unknown exponent. Okay, the formula for this particular one to go from the exponential form, which is 10 equal 2 to the x, is going to be x is equal to log base 2 of 10. Now, before the TI-84, you had to do the change of base formula. The change of base formula is really good to know and is very helpful. We do utilize this as we look at the algebraic aspect of a multiple choice question, for instance. So I need you to know the change of base formula, which is written here. In the calculator, you can certainly type in the change of base formula. So for instance, in our calculator, we have the natural log, which is base e, and we have the the common logarithm, which is base 10. So we wouldn't be able to do in the past this problem because it's log base 2. We would have to have the change of base formula. So in this particular case, let's say that we want to change it to log base 10. So we have log base 10, which is the common logarithm of 10 divided by log base 10 of 2. You also could write it as the natural log of 10 over the natural log of 2. If you wanted to, for some odd reason, you could do the log base 50 of 10 over log base 50 of 2. In your calculator now, with most of these newer calculators, the TI-84s, if you press the math button and if you scroll all the way down to option A, there's a log base button that allows you to change the base to anything you want. So you could simply just type in log base 2 of 10. But again, you need to know the change of base formula for some of the multiple choice problems where you don't have a calculator available. Okay, let's talk about some properties of logarithms, some really common ones. First off, we have log base a of a. That is going to be 1. Log base a of 1, that will be 0, because a to the 0 is 1. And a here is just a numeric value. And we are assuming that a is not negative or 0. Log base a of a to the x, there's a property that says that we can take that power of x and bring it to the front of the logarithm. And so therefore you get x times log base a of a, and since log base a of a is 1, you simply get x here. This one's a little bit goofy. The logarithm is in the exponent, and so this property says that you have a to the power of log base a of x, and that simplifies simply to x. I've seen some problems in the past in the AP exam where it's stuff like like this, and that is simply just 2. So sometimes that is utilized. It does depend on the problem, but I know in like differential equations, when we do chapter 8 in A-B calculus, that type of algebra does come up once in a while. Okay, the next one is to simplify or expand a logarithm. So if you have a number 5 log of the quantity a times b, you can rewrite that as log of a plus log of b. And sometimes that's useful depending on what we need to do with our problem. For number 6, there's really nothing we can do with that. It's very tempting to try to do some of the other properties, but we're unable to. With number 7, we're going to get log of a minus log of b. With number 8, it looks a little bit like number 7, but it is definitely different. 8 is the change of base formula. So you could write this as a single logarithm with base b and argument a. And again, go back and forth there. With number 9, that kind of connects to what I was talking about with number 3. With number 9, you can pull that r, that power to the front, and that's a very common way to simplify these. So you get r times log base b of x. All right, let's move to the next page. We've talked a lot already about the natural logarithm, and you all should know how important this is for the study of calculus. It's such a common function, but the natural log of e is going to be 1, and the natural log of 1 is going to be 0. So you should just have those memorized. Okay, we're going to try some examples. So one of the things you can do here is you can pause and try some of these examples on your own. We don't have a key posted to Schoology, so this video will serve as the key for you. But you can certainly go and try these now. None of these examples are necessarily new concepts or general definitions or anything. They're just examples for you to try just to make sure that logarithms are going okay for you. So feel free to pause and then come back and check. So number 1, we're going to do the sum or difference of logarithms. So we're going to basically expand this out. We can start by taking the natural log of the numerator, so x cubed times the quantity x minus 3, and then we're going to subtract the natural log of y. That was one of our properties. Then we can expand this again using another property, so the natural log of x to the third plus the natural log of the quantity x minus 3 minus the natural log of y. And if we needed to, we could expand this one step further and pull that power down. And I think this is about as far as we can go on this particular problem. So I'd say that's our expansion of that problem number 1. For number 2, this is one of the properties that we had. That's just 5. Number 3, super similar to number 2, but those parentheses change everything. Log base 2 of 2 is 1. So this is the equivalent of 1 to the 5th power, which is 1. With number 4, we want to probably simplify this a little bit. I would make this log base 27, and then 243 is going to be our argument. Actually, you know what? I'm gonna change that just a little bit. I think this will be easier for us. Let's do this. Let's leave it as log base 3. Let's write 243 as 3 to the 5th power. I think this will go better. And then we have log base 3 of 3 to the 3rd. Now remember, we can pull the 5 down in this case, and we can pull the 3 down in that case. And so log base 3 of 3 is just 1, so what we get here is just 5/3. Number 5 is really similar. We're going to utilize sort of the same technique with rewriting 243 as 3 to the 5th, and it looks like 35, sorry. 3 to the 5th power, and then 27 is 3 to the 3rd, and that gives us log base 3 of 3 squared, and our property says that we got 2 for an answer there. Write as a single logarithm, so we're going to condense this down. We can write it as a natural log of, let's see, I'm going to write this, I'm going to save a little bit of space. I'm going to do x squared minus 1 over x plus 1, and I'm going to make this to the 1/2 power. Because they're both to the to the square root, so I'm just going to take the 1/2 power overall. I'm going to pull that 1/2 to the front. The other thing we could do here is factor the numerator, which ends up canceling with the denominator. And so what we get, I think this is about as simplified as we can make it, is 1/2 natural log of the quantity x minus 1. Okay, number 7. So this is a perfect example of utilizing logarithms. So we have log base 5 of 12 equal to x plus 3. And without a calculator, I guess we'll just subtract 3. So we have log base 5 of 12 and then minus 3, whatever decimal that becomes. Okay, number 8. So this is a double logarithm, which is strange. So I'm going to first put it into exponential form. So we have 10. Remember, both of these logarithms are common logarithms, which means that they're base 10. So we have 10 to the 3rd, which is equal to log of x. So we have 1,000 equal to log of x. And I'm going to turn it into exponential form yet again. So I have 10 to the power of 1,000. Which is a very large number, equal to x. Okay, for number 9, let's combine these. So we have log base x squared plus 6 of 10, excuse me, because we're going to multiply the arguments, equal to 1. Let's go ahead and move this or change this into exponential form. So we have x squared plus 6 to the power of 1 is equal to 10. Which means that x squared is equal to 4, which means x is positive or negative 2. Always double check that you accidentally don't algebraically come up with an answer that doesn't work in the original. You can never have a negative base, negative argument. Now in this case we're okay because the base is x squared plus 6, so no matter what I plug in, I'm going to have positive values that will work in the domain. You always want to check the domain. All right, let's move on to the last page. Okay, so for number 10, this one's a little tricky. What I would do here is change each of these to a natural logarithm, logarithm by change of base. So I would do a natural log of 3 over the natural log of 2, and then we're going to multiply that by the natural log of 64 divided by the natural log of 3. And then what you're going to find is that you can cancel natural log of 3, giving you natural log of 64 divided by natural log of 2. I would actually convert that back to log base 2 of 64, and that gives us, let's see, 2 to the 6th is 64, and so we end up getting 6 as a final answer there. Okay, number 11, I'm going to do exactly the same thing. I got natural log of 9 divided by natural log of 4, natural log of 12 divided by natural log of 9, natural log of 16, you can sort of see the pattern here, divided by natural log of 12. Okay, we can, let's see, cancel, 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 cancel. We have natural log of 16 over natural log of 4, which is log base 4 of 16, which is log base 4 of 4 squared, which is 2. All right, almost done. 2 more. So here we have the square root. So we have log base 4 of x could be equal to 4, or it could be equal to negative 4 because we're taking the square root of a square, which we know is the absolute value. So in this case, we get 4 to the 4th, which is 256. In this case, we get 4 to the negative 4th, which is 1 over 256. A little bit tricky there. Okay, last but not least, let's see. Let's do log of x. We'll leave the left side, square root of that. And then remember how we can pull that power to the front, and we get 1/2 log of x. I'm going to square both sides, so I get 1/4, and I have log of x squared. I'm going to set equal to 0. You always want to set equal to 0 and then factor and solve. It's just the way we got to do things. You don't want to ever lose a solution. So I'm going to factor out a log of x. Get 1/4 log of x minus 1.
Now we're going to use the zero product property to identify our solutions. So first we have log of x equal to 0, and that will occur when x is equal to 1. So there's one solution. And then we have 1/4 log of x minus 1 equal to 0. So we have log of x equal to 4, and this gives us x equal to 10 to the 4th, which is 10,000.
Okay, that's going to do it for section 1.6. Thank you.